Welcome to day 3 of Unit 6, Variation. Asynchronous. Awesome. Don't we love that? So today we're going to talk about different types of variation. You might have done a little bit of this in Algebra 1 with direct variation. Y varies directly with X, okay? And that just means that as X increases, Y increases, okay? It's a direct variation. Okay, an example of a direct variation in real life is maybe the more hours you study, the higher your grade is. The amount of hours study goes up, the grade goes up. Okay. Inverse variation, as y varies inversely with x, you can see there's these equations that are associated with it. X times y equals k. Okay, and it's important to note that k stands for, k stands for constant. A k is a constant. It's called the constant of variation, which might seem like an oxymoron because how can something be a constant of variation? But that's what it is. So in an inverse variation, the product of two variables is constant. In direct, it's the ratio of two variables. For example, x times y equals k. So think about this. If you had 7 times 2 equals 14, so k was 14, right? So x is 7 and y is 2. Well, what happens when x is 2 and then y has to be what? So it equals 14. Of course, y would have to be 7. So x decreased, y increased. Inverse variation always has to multiply to the same number. Direct variation always divides to the same number. You might also look at that equation for direct variation, say that looks like the slope of a line with a y-intercept of 0. Joint variation, the ratio of variables is constant. So it's very much like direct variation, except instead of one variable, there's multiple variables, okay? Frequently just two. So z varies jointly with x and y, okay? The cost of a cake is jointly variable to the radius of the cake and the thickness of the cake, right? Those two things, if it was at a bakery, those two things, the cost of a cake would be jointly variable to the thickness, how thick the cake is, and how round the cake is. And then, of course, combined variation is the last one. And those are a combination of variations, joint and inverse. And the equation is really what you're going to want to know. These equations are what you're going to want to learn. So z varies directly with y. So notice in direct variation, y equals k times x. Here, z equals k times y because z varies directly with y, inversely with x, okay, over x. You could multiply them back together. X times z equals k, right, to make it look like either of those inverse equations, okay? Direct, inverse, joint, combined. Those are our choices. Got to memorize those equation starting points, and always have to have a K for constant. Some of you are saying, Mr. Schaefer, constant starts with a C. I'm aware, but I'm also aware that math wasn't invented in English, so anything is possible. Okay, so let's do a couple of these problems, and then we'll start you on your way. The period of a p of a pendulum, the time back and forth, is directly proportional to the square root of the length. So please note that right there, square root of the length. If a pendulum is 1 meter long, has a period of 2 seconds, what is the length of the pendulum with a period of 6 seconds? So the first thing I want to do is create an equation with the very first sentence. So the period of a pendulum is directly proportional. So is tends to tell me that I want to have an equal sign, okay, is directly proportional to the square root of its length. So we got to have k times the square root of L, okay? Or you can say P divided by the square root of L equals k. Doesn't matter either way, either one of those direct proportional statements applies. Okay, so the first thing we always want to do, solve for k. Solve for k. Okay, so we're going to substitute in. If a pendulum is 1 meter long, so I'm going to put in 1 for L, I'm going to use that first equation. I got k, and has a period of 2 seconds. What does k equal? Okay, so you could say k is equal to 2 divided by the square root of 1, which we would then say k is equal to 2. Okay, so once we know k is equal to 2, we're going to substitute it back in. It doesn't matter which equation you substitute it back in. I'm going to use this equation here because it's already got the k. So I know this equals 2. What is the length when the pendulum period is 6 seconds? So the period is 6 over the square root of L. Okay, so I can cross multiply. 2 square root of L equals 6. The square root of L equals 3. Square both sides, L equals 9 seconds. Okay, and the reason it equals 9 seconds is because that proportion is the variation is always a constant. Okay, basically 1 is to 2 as 6 is to 9 in this case. Okay, based on our constant k. Okay, so number two. If y varies directly as the cube of x, and y is equal to 8 and x is 20, find y when x is 25. Y varies directly as the cube of x. So remember, there's a couple ways I can write this. I can do the divide. Y varies directly as the cube, and that equals k. Or I could say y equals k times x cubed. Okay? These things go back and forth. It does not matter which one you use. Whichever one's more comfortable, maybe easier. Okay, so when y is 8, x is 20. And that equals k. Okay, and that gets to be 8. 20 cubed is just 8,000, not just, but so that is 1 over 1,000 for k. So k is 1 over 1,000. Okay, there's my k. Once I know that, I want to know when x is 25, what happens to y? Okay, so I can use either equation. I'm going to use y equals, because I'm solving for y, k, 1 over 1,000 times 25 cubed. So I'm using that version of the equation. And that becomes, I'm going to rewrite it. You can do a lot of things. I'm going to rewrite this as 25 over 10 cubed. But there's a lot of ways to skin the cat. You could cube 25 and divide it by 1,000 if you know 25 cubed. But this is a little nicer because this is going to reduce really nicely to 5 over 2 cubed. And that's going to be 125 over 8. Now, if you had a calculator, certainly that would be something you might use a calculator for. But remember, the best calculator is your brain. Okay, so y equals 125 over 8. Okay, so direct variation. Y varies directly as x. As y increases, x increases. Okay, and notice in this problem, y went from 8 to 125 over 8, and x went from 20 to 25. Okay, they both increased by a proportion that direct proportion. Okay, excellent. I love these problems. I love a good word problem, right? Who doesn't? And I know that the answer is everybody does. Okay, now number 3, inversely proportional or varies inversely. Okay, x varies inversely as v, and x is 48 when v is 8. Find x when v is 64. So let's make our inverse variation equations. We can say x times v equals k, right? Because I've always got to have that constant of variation, k, constant of variation. Or I could say, right, I could say x is equal to k over v, okay? And I'm going to erase that symbol here in the middle because I don't even know what that looks like. But I tell you, it was supposed to look like that. That's still not great. Okay. So when x is 48, v is 8, solve for k. First step always, solve for k. Okay, solve for k. Got it. Game changer. K is equal to 8 times 48, which you know is 384. And if you don't know it's 384, you put it into a calculator and you pretty quickly figured that out. Okay. So now, when v is 64, what is x equal? Okay. Now, notice that v has gone from 8 to 64. So our expectation, since they vary inversely, is that x is going to decrease. The value of x should decrease. Okay. And we can put this into x is equal to k, 384 over 64. And I know you all have a calculator, but if you didn't, you'd be like, oh, I think that's about 6. And turns out you would be correct. X is 6. Okay, x is 6. So because it was inverse, we notice that v increased, x decreased by a proportion consistent with the constant. Okay, by a proportion consistent with the constant. Notice that v multiplied by 8 and x divided by 8. Pretty cool. If you haven't hit pause yet, then keep going because this is going to be a good one. Okay. If the force acting on an object stays the same, then the acceleration of the object is inversely, ooh, that's the big word, proportional to its mass. So acceleration and mass, okay? So I'm going to say A is acceleration, and I'm going to say M is mass. Pretty sure that's pretty constant. Okay. If an object with a mass of 9 kilograms, so there's my mass, accelerates at a rate of 9 meters per second, okay, so there's my rate, meters per second squared, by a force, find the rate of acceleration of an object with a mass of 3 kilograms that's pulled by the same force. And so the same force, that's part of the equation just because, you know, science tells it has to be. But it's not, I mean, it's important to the problem in the sense that we can do the problem, but it's not going to figure into our equation. So don't get caught up with that. Okay. So we know acceleration times mass equals a constant because they're inversely proportional. Or we could say, let's see if I can make this one better this time. What do you think the odds are? Very good, because I did it. Acceleration is equal to the constant divided by the mass. Either one is fine. Either one of those is fine, okay? What's the first thing we always want to do? This is the point in class where the kids in second period would type into the chat to tell me the answer, and the kids in eighth period would type and yell into the microphone. So if that's what you do your thing right now. What do we always solve for first? Yeah, K. Thank you for that. So we know that the acceleration is 9 and the mass was 9. So that's going to give me a K of 81. Okay. Now we say, when the acceleration is unknown, the mass, what's the mass when the acceleration is 3? Okay. So notice that the mass has decreased, so we would expect the acceleration to um, or increase. Okay, and we know that acceleration is equal to k divided by mass. So the acceleration is equal to 27, and we know that's meters per second squared because that's just the labeling we use for speed there. Okay. Think about our stuff that we did in Unit 3 when the word problems. Okay, notice, oh, that decreased by a factor of 3 and that increased by a factor of 3. And that makes sense because it's got to be inversely proportional. One increases, one decreases. Okay, now is the time in class where people would say, could we get a break? And I'm like, sure. Hit the pause button. We're not quite halfway, so maybe you hold off for one more question. Maybe you don't. I don't know. Okay, number 5. The weight of a body above the surface of the earth is inversely proportional to the square, that's important, of the distance from the center of the earth. What is the effect of the weight when the distance is multiplied by 8? Okay, so the distance is multiplied by 8. So we're going to say the weight, and you can make up any variable you want. We're going to let weight equal W, though. That seems like a good idea. And then our old friend distance will let equal D. You can make capital D, lower d, it doesn't matter. Okay. Weight is inversely proportional. Weight times distance equals K. Oh, the square. The square of the distance. Good catch by me. Okay, so no one has to raise their hand and say I did it wrong, and I appreciate that. Okay, the other way you could say this is W is equal to the constant over D squared. Okay, the distance squared. Okay. What is the effect? What is the effect on weight when the distance is multiplied by 8? So what is the effect on weight? So let's look at this and say, okay, weight is equal to K, and we're going to multiply the distance by 8. And remember, that's squared. So K becomes 64 distance squared, or excuse me, K over 64 distance squared. If you want to go back to the original, because we want it to look like this at the end, I'm going to multiply through by 1/64. So I'm going to get 1/64 W equals K over D squared. Okay, I just divided both sides by 1/64, and that equals W. So what's the effect? The effect is the weight is divided by 64. Okay, so if the distance is multiplied by 8, but I'm squaring it, it's really being multiplied by 64. And then I'm going to have a division by 64, right? Because it's inversely proportional. Okay, 8th period, folks, you can take your Persky pause. 2nd period, folks, we're going to take a brief break. And in order to do that, of course, you're going to have to turn off the video. Okay. Welcome back. I hope you enjoyed your break. The volume of a geometric, we're going to continue on. We're going to crush this. The volume of a geometric figure varies jointly. Okay, we haven't seen that one yet. So we're going to look back to page 1 to remind us what joint variation looks like so we can write these equations. The volume, okay, the volume, so I'm going to say volume V, jointly with the square of the radius, That's going to be my r, okay? And the base of the height. So I'm going to do that. The square of the radius of the base and the height. Sorry, let me read that better. With the square of the radius of the base and the height. Okay, so joint variation, couple ways of volume is, okay, and then we're going to say the radius squared, okay, the square of the radius of the base and the height, and that's going to equal k. Okay, notice this is a direct variation with two variables. So you could also write it, as volume is equal to k r squared h. So that's the equation for the volume. Either one you could do. Estimate the constant of variation if v, so basically we're just going to try to solve for the constant of variation. So we're going to estimate for the constant of variation if v is 63.333, 63.33. The radius is 2.4, and I'm squaring that. And the height is 10.5. And what do we get? Well, you get 1.047. That's approximately K. I would point out an interesting figure to you. Spoiler alert, or trigger warning, really, geometry lesson approaching. So if you don't like geometry, fast forward like 20 seconds. But note, pi over 3 is equal to approximately 1.047. So volume is equal to pi over 3 r squared h, and that's the volume of I said that's the volume of oh, cone. Yes, cone. Very good. Cone. Excellent. Whew. Who knew that it varied jointly with regards to stuff? Who knew that there was actual math and geometry last year? Raise your hand if you knew that. I know when I was in geometry, I definitely did not know that. Okay. Joint variation. Number 7, the time in hours it takes a satellite to completely orbit the Earth varies directly. This feels like a combined variation because there's a lot of words, so I feel like more is coming. So the hours it takes time, so I'm going to say time is t, a satellite to complete an orbit around the Earth varies directly as the radius of the orbit, so r for radius, from the center of the Earth, and inversely as the orbital velocity. Let's put that at a v. Ooh, orbital velocity. That sounds high tech. If a satellite completes an orbit of 820 miles above the Earth 11 hours at a velocity of 22,000 miles per hour, how long will it take the satellite to complete an orbit if it is 14,000 miles above the Earth at a velocity of 36,000? Use 3960 as miles as the radius of the Earth. Rounded to the nearest thousandth th of an hour. Okay, so come up with an equation. The time it takes varies directly. Okay, so time is equal to, and we've got our constant because we know that varies directly with the radius, kr. Okay, and inversely as the velocity, the orbital velocity. Okay, t equals kr. That's a that's an equation for direct variation with time and radius. And t equals k over v. That's an inverse variation with time and orbital velocity. Okay. What's the first thing I should always solve for? I know, you guys said it before, so let's say it again. You're right, K. You're right. So if a satellite completes an orbit 820 miles above the Earth in 11 hours, so our time is 11, 820 plus 3960, because that's the radius of the Earth plus 820 miles above, so the orbit is above the Earth, all divided by 22,000. So you could say, if you want to just dump this in the calculator all at once, 11 times 22,000 divided by, sorry, 820 plus 3960. And I'm doing this step by step. Obviously, if you're doing this in the calculator, you're going to simplify like that. Okay. So you get 12,100 over 239. Does that simplify? I don't know. Probably not. Do I got more work to do? Yeah. So, and did it say round? It sure did. So am I worried about that right now? Simplifying that? I am not. I am not. Okay. So now, how long would it take? So time, we got our K. If 1400 plus the Earth's orbit or Earth's radius over 36,000 miles per hour. So notice two things are happening. Like we can't say time's going to increase or decrease because something that relates directly to it, the radius is increasing, but something that relates inversely to it, the velocity is decreasing. So two things are acting on the time, and so we'll see what happens, and we multiply all that out. I'm doing this in my head. If you believe that, you don't need to come to class anymore. You shouldn't believe that. So time is equal to, and we did 1,000, so 7.538 hours. So time dipped just a little, right? But we had something go up, so time would have gone up, but we had something that's inversely proportional go up, and so time would go down. So it almost balanced out to be the same. Okay, two more, folks. Two more. We're gutting it out. You guys is a gutty performance today. You're putting in the hours. I appreciate that. Y varies jointly as a, b, and inversely as the square root of c. Whew, that's a lot to think about. But as soon as I see that y equals varies jointly, I'm going to do y equals k times a times b. And inversely as the square root of c. Remember, inverse the square root of c. Okay. Could you solve this for k? Well, of course you can. Y is 70, because we're always solving for k. K is k, A is 7, B is 10, C is 9. Okay. And if you do this, you're going to end up with 1 equals k over 3, right? Because you get 70k equals 70 over 3. Yep. So k is 3. The constant of variation is 3. Okay. And then the old what happens when? Okay. When y is equal to, find y when a is equal, so find y. I love when it's find y. I don't have to do any work. So k is 3, a is 5, b is 3, c is 4. Okay. y equals KAB over square root of C. Now, the joint variation things, right? A and B both decrease, so I would expect C to decrease. 9 decreased to 4, that's the inverse, so I would expect y to increase. So y should be, there's some parts that are making y increase, and there's some parts pulling y to decrease. We'll see what has the greater effect, and we end up getting y equals 45 over 2, which seems like a pretty good answer there. Some of you are like, well, that's 27 point, it's not 27 point anything. That's 22.5. There, I made my mistake for you guys. I hope you're happy. Okay, last problem. You're like, this is an asynchronous day, Schaefer. Why are we sitting watching this video for so long doing notes? I know. Good news is you're going to get to start on homework soon, um, and maybe do a marble slide. I don't know. It's a crazy day. Okay, example 9. The volume V of a given gas mass mass of gas. The volume V of a mass of gas varies directly as the temperature. So I always start writing as soon as I see something I understand. It varies directly as the temperature. Volume varies directly, y equals kT, and inversely as the pressure. You could message me and tell me what law this is. This is a law, but if you guys, I think you have to be in chemistry for this law. So if you're a sophomore, maybe you know what law we're talking about here. And inversely as pressure. So inversely as pressure varies directly with time, temperature, and inversely as pressure. A device is calibrated. So what's the first thing we're going to do? Solve for K. It's almost like you heard a whisper in your ear saying, solve for K. And that person, that's probably your inner voice, really, is what I'm thinking, isn't wrong. The inner voice is right. Let's do a little solving for K, which, as everyone knows, stands for the constant of variation. So the volume, 250.8, is equal to K times the temperature, 570 degrees, over the pressure, 25. Okay? You do a little solving. You end up with K is equal to 250.8 times 25, all divided by 570. I just rearranged it, and that gives me 11. Again, use your calculator. I know you got the best calculator up here, but use the Desmos or the one on your desk, not the one up in your head. What is the volume of this device when the temperature, there's my new equation. What's the volume of the device when the temperature is 310 degrees and the pressure is 10 pounds? Okay, so volume, 11 times 310 divided by 10. What do we expect to happen? Well, let's look. The volume, the pressure went down. So inversely, I would expect the volume to go up. They have an inverse relationship. The temperature went down, and the temperature and the volume have a direct relationship. So I would expect that to cause the volume to go down. So again, acting in opposite directions on this. And when we multiply this out, we get the volume equals 341 pounds per square inch, or inches cubed. And I don't know why I wrote 340. But I do mean 341. 341 inches cubed. Okay? It seems sad that this is over. It seems exciting that you should now get started on the 2 things you're supposed to do for homework that are posted in Google Classroom.